So, let us talk about lecture 12 in module 1 of dynamics of ocean systems. We have solved this example yesterday. We have derived this equation of motion using Newton's method. We actually prepared a free body diagram. We substituted the external forces acting this mass and this mass separately. We arranged the equation terms and we got this matrix arrangement, and we also discussed that this is very easy format to remember, but still one should understand how they can be derived from the fundamental understanding. I will go by the same problem. I will take the second method by which we can even write the equation of motion, let us say by energy method. The energy method says d by dt of partial derivative of kinetic energy with respect to du qi dot minus partial derivative of kinetic energy with du qi plus partial derivative of potential energy with dou qi plus partial derivative of dissipation energy with dou qi dot should be set to qi, where I is the number of degrees of freedom and qi is the force vector, and ke represents kinetic energy. For a spring mass system, it is half m velocity square. P represents potential energy. For this particular example, it is k x square, and dE represents dissipation energy. In this example, of course, it is not, but it is half Cx dot square. This example is not applicable because there is no dashpot or damping attached to the model. This equation is very simple. What you have got to do is you have to first find the expressions for kinetic energy, potential energy and dissipation energy separately, and find the partial derivative. One may ask a question, why partial? This is of course applicable to multi-degree freedom system model. For example, if you take this particular spring, it is connecting both displacements x1 and x2. So, when you write an equation, both terms x1 x2 will be involved. So, both degrees are connected or integrated by one particular member. So, you look at one degree of freedom at a time. So, partial derivative with respect to that particular displacement function, and you take a derivative of that and you equate this, and you do this so many number of times as I, where I the numbers of degrees of freedom. So, if you want to try to apply this equation as such to this problem, first thing what I will understand is I will be 2 in this case, because there are 2 degrees of freedom. So, I will write 2 equations now. One equation with respect to q1 or x1, other equation with respect to q2 or x2. Okay. Let us write both the equations. So, first let us write the equations for kinetic energy. So, look at this spring, it is not connected to anywhere else except x1. So, half m x1 dot square plus half m x2 dot square. Now, potential energy half 2k, that is this spring connecting only x1. So, x1 square plus half k, that is this spring connecting these two. Now, as the same norm follows, we can say x1 minus x2 the whole square, or even if you write x2 minus x1, since you are squaring does not matter. Okay. Now, dissipation energy is not there because C is not present in this case. I do not have to write the equation for dE. So, these are the two expressions I have, which has got variables as x1 and x2. I take a partial derivative of them. So, let us try to do this separately. So, for I equal to 1, for I equals 2. Let us do it separately. So, I must first find dou kinetic energy by dou qi dot, that is required. So, I see this equation. So, I instead of say I should say q1 dot. Q is the displacement here, x1 or q1. So, it is going to be half of 2m of x1 dot. So, I should say d by dt of this function, that is required here. So, I should say m x1 double dot. Okay. Then I must require dou kinetic energy, that is partial derivative of this with respect to qi or q1. In kinetic energy, I do not have a term related to displacement, all terms are related to velocity. So, 0. Then I should say potential energy with respect to q1. Potential energy is here and q1 is there in both equations. So, let us do it here, which will be half of 2k of 2 x1, okay, plus half k of twice of x1 minus x2 of 1. So, let us simplify this, which goes 2k x1 plus k x1 minus k x2, which becomes 3k x1 minus k x2. Okay. Let us do it for x2, that is I2. So, kinetic energy with respect to q2 dot, which is half m x2 dot, that is the term here, because that becomes 0. I am taking a partial derivative. So, d by dt of this term, which will give me 2 here. So, m x2 double. So, kinetic energy with respect to again 0, because there is no term related to q2. Potential energy with respect to q2. I come to this equation. Of course, there is no q2 term here involved, only in this case. So, half of k of twice of x1 minus x2 of minus 1, which becomes minus k x1 plus k x2. So, I retain this part, I will remove this. Okay. I have to rearrange this in this form. 2 equations I will write now. So, let us write the equation with respect to 1 first. So, this term I am having it here. So, I should say m x1 double dot, this term is 0, the second term is plus 3k x1 minus k x2, and of course, the force applied at the first degree externally is 0 in the problem. Okay, there is no force applied. So, 0. Now, I write the second equation where I is equal to 2. So, look at there, m x2 double dot minus k x1 plus k x2 equal to 0. I can now rewrite this in a matrix form, m 0 0 m of x1 double dot x2 double dot plus 3k minus k of x1 x2 is 0, which is same as the equation of motion what we have in Newton's method. Okay, one can do it like this also. Let us do one more problem. So, let us say example 2. One was both the cases solved using, deriving the equation of motion. Example 2, I want to find the fundamental characteristics of dynamics for a given spring mass system. There is a data given to me. The data says, data given to me is this. Let us say mass in SI units is 4.5 kg damping coefficient is 0.12 Newton per meter per second, viscous damping, and stiffness of the spring also given as 30 Newton per meter. These are all SI units, this is data given. What is required? What is asked? They wanted to find out the natural frequency of the system, wanted to find out the damping ratio, they wanted to find out the damped vibration frequency of the system, they wanted to find out logarithmic decrement of the given response, decrement because damping is present. So, it is a damped free vibration model. So, we already know omega n, solution is simple, standard equations are there, omega n is square root of k by m. So, let us substitute k and m in the respective units and try to get the value, which is square root of 30 by 4.5, 2.581 radians per second. I can quickly find Cc, which is critical damping. Why? I want to find zeta, zeta is a ratio of C versus Cc, C is given here, I can find Cc, therefore I can zeta. From the equation what we discussed yesterday, it is 2 m omega n, we already know the values. So, 2, 4.5 and omega n is just now known 2.582, 23.238 Newton per meter per second. Now, I can find zeta, which is the ratio of C over Cc, which is 0.12 by 23.238, 0.516%. So, we have seen two examples, we will see example 3 now. Let us say in a simple spring mass system, if it is a single degree freedom system model, we can easily find the natural frequency of the system using this expression, which is k by m. It means k and m should be uniquely defined. If we are able to do that for a given system, we can easily find the frequency of vibration, whereas k is in Newton per meter and if m is in kg, this will be in radians per second, you can easily find. But there are some systems for which k cannot be or m cannot be easily quantified. Okay. We will take an example of that kind and see, then in that case how do I know k? Okay. So, let us understand stiffness is defined as force for unit displacement. So, the algorithm is very simple here. If we really wanted to derive stiffness matrix or stiffness coefficient of a given matrix, give unit displacement to the system at the points where you want to and try to actually find the forces in each member, right. I apply the same concept here for a problem and see how we can do this. So, we all know that, let us say if I have an offshore platform, maybe even a jacket, is a template structure. We all know as a structural engineer or the person who understands strength of material, if for example, there is going to be a deck here, the deck needs a support system which will transfer the load from the top side to that of the ground or to that of the support system. Let us talk about this particular system, which is typical truss system. So, it is going to be a complicated truss system, but I will take a very simple truss system and try to demonstrate how to get the natural frequency of this system where k and m is not readily available in the system. Okay. So, I will take a very simple example of this kind. Let us say I am marking a simple truss system like this. If you ask me a question, what is the relevance of this truss system to that of this is a complicated truss system where we cannot analyze it now, it will take a lot of time, but the same algorithm and principle can be used for the system as well. We will take a simple example. So, obviously, there will be a support system. My support system is given like this. We will name the joints, let us say A, B, C, D, E and F. These are all called joints or sometimes called as nodes. Let us say the mass of the entire system is suspended at this point and it is known to me. You can easily find this mass, because if it is a given system, if you know the cross section dimensions of each member, if you know the density of the material, if you know the volume of the material, you can find the Cg constant of every material, you can take a summary and you can find y bar and x bar, you know where m is acting. So, W is mg, you will actually know W, so divide by g you will get m. So, m is known to me. M may not be exactly at this point, m may be somewhere here which is Cg of the entire system. Okay. So, m is known to me, but you see different members have different axial stiffness. Okay. The axial stiffness of every member is given by simply AE by L, where A is the cross section area of the material or the member, E is modulus of elasticity of the material and L is the length of the member. So, if you work out the units here, let us say mm square, Newton per mm square, mm. So, ultimately the stiffness will lead to this unit which is as same as force per deflection. Interestingly, if there would have been only one member here, I could take the AE by L value of that member and I can find easily K, I know m, I can find the natural frequency of vibration of that member or the structure. But here the structure is assembly of different members. Now, A may be different, we do not know. E sometimes may be different, but generally it is not different, but L is certainly different. For example, if it is a square system of 45 degree, L of these two may be same, but obviously the L of this is different. Therefore, axial stiffness imposed or possessed by each member is different. Then what would be that net K of the entire system which will contribute to the numerator here to find omega. So, it is an argument now. If all the members are parallel, you can say K equivalent. If all members are series, you can say K equivalent. Now, here there are members which are neither parallel nor series. So, we cannot find easily a K equivalent from a standard expression. I want to know K equivalence for this, then only I can find omega n. Okay. So, it is a very interesting applied mechanics problem on dynamics as a simple example. So, I will use unit load method which we already studied in structural mechanics principle, but I will apply this for dynamics, that is a very interesting problem. So, I will take up this particular issue or this problem and say I will find out the forces in each member. So, if this is, let us say the truss given to me, let us say this angle is 45 degree, support system is known to me, I take this as W as a known value for me. I call this as L. Obviously, this is also L because it is 45 degree. I will open up a table now. Member nomenclature. You should also have an order of marking the nomenclature. This is called Bowes notation. You must be recollecting this in structural mechanics. This is called Bowes notation. Bowes notation is an algorithm given for marking the legend or nomenclature of nodes. So, I am following an order of clockwise. It is not advisable to say A, B, C, K, F, no, you have to have an order. Okay. So, first for the given force, let us find the external reaction. Fortunately, in this case the truss system is determinate. If it is not determinate, there are methods to solve, but let us know. If it is symmetric, therefore, this is going to be W by 2 and W by 2, okay. Because it is symmetric, it is determinate also, we can easily find. So, let us pick up any node, we should not have more than 2 unknowns. Now, the question comes here is, what are the unknowns? All the axial forces in each member is an unknown. Now, you are deviating to a thinking of structural mechanics, because talking about dynamics. Dynamics, we are not interested in forces, we are interested in stiffness, which is rather equivalent stiffness. Then why we are talking about forces? Why? Because stiffness will become a force when I give unit displacement. So, I will give a unit displacement at this point and try to find the forces, I get stiffness. Okay. So, I have to find the forces. So, what are the unknowns? Internal forces in each member becomes an unknown now. Okay. So, I can use or solve this using method of joints and method of sections. Method of joints is very powerful tool, easy. The method of joints rule simply says pick up any node or a joint where there are not more than 2 unknowns. It means not more than 2 members should meet whose forces are not known. Now, the question is, what are the nature of forces in these members? Truss is an axial system. Therefore, the forces in these members will be either axial tensile or axial compressive. Okay. So, let us take up node A. This is node A. I have an external force W by 2. I have a nomenclature. I write force this member, force A B. One can write force B A also, does not matter. Since I have taken the node A, I am writing A B. Okay. Similarly, this will be obviously force A F. Okay. So, I am going to make an algebraic sum of these forces. Algebraic sum means there should be a sign convention. I have to have a nature of these forces. I can assume anything. Let me say I am assuming this as compressive, this also as compressive. Now, one must really know, I have already told you this, in a truss member, if these are the nodes, in a truss member, if these are the nodes, if the member is pulling both the nodes, it is tensile, the member is pushing both the nodes, it is compressive. What is the influence of the member on the node will give you the category or nature of the force. Obviously, we also said earlier that kindly do not mark like this. Okay, this is having no meaning. That is, the member is pulling one node or pushing one node, unidirectional. Okay, this is not correct. This is vector algebra. Talk about this. So, I have to assume the nature. So, I have taken this. Obviously, it is understood that if you put compression here, it is going to be compression here also. If you put compression here, it is going to be compression here also. So, I say compression is positive. Okay. So, I quickly say that FAB is acting downward, I have sign convention. So, any force upward, any force right is positive, okay, is downward. So, minus FAB plus W by 2 is 0, that is sigma Fy 0. Algebraic sum of all forces in y direction or y axis is 0. So, I apply minus FAB plus W by 2 is 0, which gives me FAB as plus W by 2. This plus indicates that the assumed direction of the force is right. The plus does not indicate that the force is compressive. Please understand very carefully. I already said compression is positive, but this positive does not mean that FAB is positive. This positive means that the sign convention assumed by you is correct. Okay, so it is correct, so I mark it here and I say this is W by 2. Okay. Then I also write sigma Fx0, algebraic sum of all force in x axis at this node. So, minus, because the right hand side is positive, Fa0 implies that force on FAF member is 0. So, this is a null member, it has no force. Then one can immediately ask a question, why this member should exist, because it is a null member. For the given system of combination of forces, this is a null member. If we remove this W, suspend W somewhere here or here, then this may not be a null member, number 1. Number 2, arrangement of members is not only take care of forces, but to establish stability in the given system. Okay, we will not move further on mechanics, we will stop here. So, you cannot remove this member. What we are interested is to know is this member is a null member, it means it does not carry any force for the given arrangement of forces. Okay. So, from symmetry, because F is acting at the center, from symmetry I can expect this will also be of the same nature, which is W by 2, and this is also a null member. This is by symmetry. Okay. Now, I can go to node F. Node F has got these 2 members solved, but there are 3 more members. I should always go to a node where there are not more than 2. So, I cannot work at F. Okay. I cannot work at C because 3 are unknowns. Now, let us see B or D. B has got 3 members, but this force is known to me, there are only 2. So, I can pick up B, solve B and get the value. Can you give me the value of M FB or MBF and MBC? That is FBF and FBC. Work out and tell me what is the value. So, this is going to be W by root 2. Similarly, it is expected that this will also be W by root 2, and this is going to be compressive of. Okay. Now, I can pick up joint F or node F. There are 5 members 1, 2, 3, 4, 5. I can read the members FA, FB, FC, FD, FE, Bausch notation, read clockwise, FA, FB, FC, FD, FE, Bausch notation clockwise. Now, out of which FA, FB, FD and FE are known to me. Okay, there is only one unknown here, I can easily solve. So, what is this value? So, it appears that these 2 will resolve and cancel, these 2 will resolve and equate. So, this also becomes a null number for this arrangement. Okay. I want to tabulate these values, right. So, member forces. So, I start from here, let us say AB, BC, CD, then DE, EF and FA. So, 1, 2, 3, 4, 5, 6 member, then FB and FD, FP and FD and FC. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, there are 9 members. So, compression is positive, tension is negative. Let us look at AB, compression, positive W by 2, okay. Similarly, BC, just fill up this. For clarity, I will just rub this and write it on the top. This is L and L. So, these are the forces capital P, and let us write down the length of the members. AB L, BC L, CD L, L. These are all L, and this is root 2 L. Now, the internal forces in each member because of W applied here is given here. Instead of W, if I apply unit force 1, okay, that is called unit load method. Apply 1, then I will say it is a small p, and it may not actually work out. Wherever W is there, replace with 1. Try to find out Muller-Bristol principle, P L by A. So, you can, for example, this will be W L by 4 A E and so. Okay. Fill up the column. Try to find the sum of this column. Sum them here. So, this value. So, let us write it here. So, delta is P L by A sum 2.414 by A, yeah. Okay. So, I am interested in not finding the forces, but I am interested in finding out the stiffness, equivalent stiffness. So, I should say equivalent stiffness is the force when the displacement is unity. So, I am interested in finding the force which will cause the displacement is 1 times of AE by L of 1 by 2.414. Okay, I find this 2. This is nothing but my K equivalent, which is okay 0.414 AE by L Newton per meter, if provided all units are sufficing this. K is known to me and W is mg, therefore, m is W by g. We know this omega n is root of K equivalent by m. I know this. So, now you know at what frequency the system will vibrate if the structure is simplified as a single degree freedom system model as a spring mass system. Why single degree? Mass is lumped only at 1 point single degree. Okay. So, it is a very simple application of basic structural mechanics on dynamics to find frequency of vibration. So, this method can be solved for any applied for any complicated truss system also, provided you are able to solve the truss system to find the internal forces using unit load method, or there are other methods also. We will not touch upon that, but it is a demonstration, we must know this. Okay. Any doubt here? Remove this. Is it clear how to get omega n? Now, we will take example 4. Here I have got slightly a tricky problem. Let us say I have got a fixed beam but with varying moment of inertia. Depth is varying actually. We know inertia is b dq by 12. So, depth varies, I varies. Okay. So, let us say this is my I, this is 2y, twice of this, and this is L by 2 and L by 2. This joint is A, this is B. There is no joint here. I just drawn a dotted line just to show that there is a difference. There is no joint here, it is a continuous beam. Yeah, I think you have seen a stepped beam like this, no? It is constructed, okay? Or you would at least for sure would have seen a cantilever like this. 100% sure you would have seen. It is a varying I, okay? Now, I want to know the equivalent stiffness of this. Why? I want to know at what vibration frequency it is going to vibrate. Let us say I idealize this at this particular location as a lumped mass I want to know at what frequency it will vibrate. So, obviously K equivalency is not known to me. W is known to me because M can be computed. I can easily find W from the cross sectional dimensions in geometry, but K cannot be easily found out. Okay. So, I want to know K for this. So, to determine omega n for the given problem. It is a very classical example in top deck system of offshore structures, because wherever you got top side crane facility, derricks, flare booms etc. located, obviously there will be deeper beams. So, you can encounter a support system where the moment of inertia of the cross section may vary, 1. 2, you can also encounter a column section where the strength of the material will vary, because Young's modulus varying from 350 till as high as 1200 is being used in offshore structural members. Okay. Therefore, strength can vary, not only the cross section, right. So, it is a very common example, classical example. So, I want to know the equivalent stiffness of the system as an idealized single degree freedom system model. Why we are doing all these things? Because by hand one should know how to compute simple values of omega n. There are other ways of also doing it. You can mathematically model this, give these properties and excite it for free vibration, you will get omega n automatically from a software also. But you must know whether the answer given by the software is right or wrong. You may not work out the answer accurately to 100% matching to the software for all 15 digits, but you must know the principal digits of the answer is right. Okay. It should not vary widely. So, you have to have a hand understanding that yes, can I model this in simplified form, can I find omega n in simplified form. So, we are looking at that, starting with this, we will move on to accurate levels later. First let us start with this knowing. Best thing is you do for the accurate level and never bother about the starting level, and you always depend on software. Whatever answer you get, you will always say the beam is vibrating at a frequency of 22 hertz, whereas the real frequency will not be 22, it will be 220, we do not know actually, and we make a mistake in design and the system will fail. So, as I picked up a dependency on structural mechanics like unit load method for finding out K equivalence here. For this I will depend on moment distribution method. Okay. That is also one of the classical method of applied to static indeterminate structures. I will pick up that method and try to solve this problem using moment distribution method. Generally, if you see moment distribution method, is applied to find out the end moments and the moment at this portion and the respective shear as a mechanics problem. But I will use this as a tool to find omega n for a dynamics problem, as we did in the last example. Okay, let us see how we do it. So, most of you may not be aware or would have forgotten or would not remember or would not know correctly how this method is applied, because you know the method name, but generally when you look at these methods, people generally dependent on textbooks and exactly follow the same steps what the author has written in the book and exactly try to solve the same problem what author has solved. You are comfortable. When some other problem is given to you, you are totally lost, because again you turn back to the author will be able to solve the problem, but you will never be able to solve the problem, because your fundamental in the mode of explanation given by the author is not conducive, you have not understood the problem actually. Okay. So, let us explain this method very quickly in a simple form first, apply to this problem, then we will move on to find out K equivalency of this problem. Remember, K equivalency is the force for unit deflection. I must obtain unit deflection at this point. Why at this point? This is the point where mass is lumped. That is the argument here. So, I will call this as joint C, let us say not a joint but a junction, intersection C. So, let us say at C I have got two members, one is CA, one is C. So, let me find out the stiffness. Bending stiffness is EI by L, that is a general formula. There are varieties of stiffness, axial stiffness AE by L, bending stiffness EI by L, torsional stiffness, there are many. EI by L, bending stiffness. Why bending stiffness? When I try to pull this beam down, the beam will bend. When I try to pull this truss down, the member will expand, not bend. Okay, depending upon the nature allowed on the member, you must use the model correctly. Okay. So, that is why moment distribution, that is why unit load method. I cannot apply unit load method here, because it is not going to expand, it is going to bend. Okay. So, EI by L is a general equation but I must say in my case it is EI by L by 2, which is 2 EI by L, because L is L by 2 in this case. Similarly for CB, again it is EI by L, but I must say it is E 2I by L by 2, which is 4 EI by L. So I must say sum of this at this joint is nothing but 6 EI by L. I must find distribution factor dF, which is k small by sum of k, which is nothing but 2 EI by L by 6 EI by L, which goes as 1 by 3. That is for the member CA, which goes as for the member C. So it is 0.33 and 0.67. So the sum should be always 1. Okay. I think we all know this. 1 by 3 is 0.33333. You can always write like this in mathematics. This is called vinculum. Vinculum means this is repetitive. This number is repetitive, infinite times. Okay, that is called vinculum in maths. So there is a vinculum number here 0.33. I pick up that number. Now this is also 0.66 vinculum, but I said 0.67 because sum should be 1. I am rounding it off. So I have the beam. I am applying at the center a deflection, which is delta. Okay. I am saying delta should be 1. Why? I am not interested in force, I am interested in stiffness. Stiffness is force for unit deflection. So I say delta is 1. The moment I say delta is 1, from the principle of structural mechanics we know that now it will apply a moment of this kind, also it will apply a moment of this kind. Now one can have a very serious question here. Sir, two questions. Why this is marked down? Why these arrows are anti-clockwise and clockwise? Okay, it is very interesting. I have a beam like this. Now this support is settled by delta, maybe any value. When the support is settled by delta, it is always understood that the structure should reach is recentering. So you have to bring this back to original. Suppose if the structure is like this, the structure raises like this, which is also delta. Now you have to bring back to the structure to normals. Suppose you have a column which is originally like this, the column goes to the right, which is delta, you have to bring it back to normal. Suppose if the structure is like this, the column is moving to the left by delta, you have to bring it back to normal. So arrow directions are not by clockwise or anti-clockwise. It is all dependent on where it is settling, bring it back. So where it is settling, bring it back, where it is settling, bring it back. Okay, so these arrows are very clear now. Why it is given downward deflection? Because I am applying mass downward. If I apply mass upward, I can give an upward deflection also. In that case, the beam would have deflected like this, and you would have marked the arrows like this. Okay, does not matter. So from mechanics we know that if delta is a displacement, the moment caused because it is delta will be 6 EI delta by L square. That is a general rule. Okay. Now one can ask me a question, when I give a deflection, how it is generating a moment? Okay. Moment is actually to be generated only at the fixed end, but how I am getting a moment here? This is not explained comfortably in many of the textbooks. It is very interesting. Imagine your hand. Okay. Keep your hand straight. There is a movie. Okay, let us not give the name of the movie. Okay, there is a movie where people used to do exercise that stretch your hand, hold a bucket of water and keep it horizontal. I mean straight. Try to keep it straight. The moment you give a displacement, you will give a pain here. You try to do that. Lift a weight, you will not feel the weight here. The pain will come here actually. Right? it will try to move to the nearest support. So, it will cause a moment actually, swinging is moment. So, this moment is because of the deflection. Same effect will also go back here, which is 60 delta V L square. Okay. This is also 60 delta V L square. This is also 60 delta V L square. Now, unfortunately, L are different, L by 2, L by 2, I's are also different. Therefore, these values are not going to be same. These are generic equations if you give displacement of delta and if the base L and this member is I. Now, in our case it is not so. Okay, we will continue this in the next class to explain what would be the moments actually caused at each section. Then how do you do a moment distribution for them, and from the moment distribution table how do you actually get a equivalent stiffness, and then from the equivalent stiffness and mass how do you get the frequency of vibration of this beam. Okay, that is our focus. So, we will continue this problem in the next class, because I will not be able to do it now, there are only few minutes left over. So, you have to understand the basis of mechanics. You must have learned there are many textbooks available for this. There are also textbooks written by good Indian authors. I have given references in the NPTEL website, please read them, and remember very carefully, dynamics is a course where what we discuss here is only maybe an eye opener for majority of the topics. If you want to really learn majority of the topics parallelly, you must open the reference material and read them parallelly, then only you will have doubts and you can ask it accordingly. Okay.